Okay, let us continue with the periodic properties of the atoms. In the last class, we already discussed the atomic radii, and we saw that there are actually three trends. So the first one is that the atomic radius decreases continuously within the period. And the second one is that the atomic radius jumps when a new period is begun. And the third one is that the atomic radius increases down a group. So atomic radius sounds like a simple concept at the first glance, but it's actually not as simple as it looks. So when you talk about atomic radius, you always need to say how you have actually defined an atomic radius so that you're making suitable comparisons. And there are actually different definitions of atomic radii, and would like to discuss the most common definitions now briefly. So overall, there are actually three different definitions, or there are actually even four. So we can define an atomic radius as a so-called covalent radius. In this case, we are talking about the radius of an atom when that atom is being bonded through a single atom to the same atom. Okay, like for instance, in the case of a chlorine molecule, Cl2, we can define the radius as half of the distance between the two chlorine atoms in the chlorine molecule. Okay, so now opposed to that, there is what is called the van der Waals radius. And the van der Waals radius is the radius between two atoms in a solid, whereby there's no significant interaction other than van der Waals interactions between the atoms. So for instance, in argon, you can define a van der Waals radius in solid argon, where there are no significant interactions between the argon atoms other than van der Waals interaction, and you define the van der Waals radius as half of the distance between the argon atoms. Okay, so now you can also define a van der Waals radius for the chlorine molecule. However, this van der Waals radius is different from the covalent radius. So for instance, you can also condense chlorine gas to make a solid, and then measure the distance between two chlorine atoms in the solid, which are not bonded bonded covalently to another chlorine atom. Okay, so you see this illustrated here. So you have two chlorine atoms. Two Cl2 molecules next to each other. And now the van der Waals radius would be half of the distance between this chlorine atom and this chlorine atom, which only have van der Waals interaction between them, not between two chlorine atoms that are part of the same molecule. Of course, the van der Waals radius is larger than the covalent radius. Okay, so now that of course doesn't work for all the elements, because not all the elements make covalent bonds with each other. So therefore, for different elements, for different atoms, different concepts for the definition of the atomic radius may be favorable. Okay. So in addition to that, you also have the so-called metallic radius. So this is again nothing else but the shortest distance between two atoms within a metal, divided by 2. Of course, this kind of metallic radius is only applicable for metals. However, metals make up most of the elements in the periodic table. Therefore, the metallic radius is actually relevant for quite a number of elements. Okay, so now in addition to that, you can even define computational atomic radii, and the atomic radius that you actually see here on this periodic table are computed. Okay, so you can take a single atom and then you can compute, well, the electron density around that atom, and you know that, and then the atomic size is defined as the volume that contains 90% of the electron density, and that then defines the radius of the atom. Okay, so when you compare atomic radii with each other, you always have to say which method you actually use, so that you do not compare apples with oranges. Okay, so you can only define one computational radius with another computational radius, or one covalent radius with another covalent radius, but you should not compare a covalent atomic radius with a computational atomic radius, for instance. Okay, so now let's go from the atomic radii to another periodic property, which is the first ionization energy of the elements. So how is it defined? It is the energy required to remove an electron from a gaseous atom. Why a gaseous atom? Because a gaseous atom is an atom that does not have any significant interactions with another atom, and therefore there are no atom-atom interactions which could cause the energy required to remove the electron from the atom to be different. Okay, so we are looking at isolated atoms here, and in practice that means atoms in the gas phase, because atoms in the gas phase have a very large distance to other atoms. So when you look at the values of the ionization energies, then they are always positive. Okay, so it always requires to remove an electron from an atom. So this is always an endothermic process. Okay, so therefore ionization energies are always positive. This also has to be so, otherwise an atom would be unstable and spontaneously lose an electron. But that would not make sense, because unstable atoms are just not known. Now let us close a look at the periodic trends. So here you see on two different graphs how the ionization energy changes with increasing atomic number. So let us first look at how the ionization energy changes within a period. Okay, so as we go from the left to the right in the periodic table within a period, then you see, for instance, for the first period, the ionization energy increases from the hydrogen to the helium. You can see this also here. Okay, and then it tends to increase in the second period from the lithium to the neon. You can also see this here. Okay, And then you see the same actually for the third period and also for the higher periods. Okay, so you see this actually here, and you see this here again, and here again for all the periods. Now you see that for the main group elements, the trend is 2 times broken. Okay, so for instance, look here in period 2, where we have only main group elements, that here we have the beryllium, which has a higher first ionization energy than the boron. And you see that here for the group 15 element, the nitrogen, we have a higher ionization energy in comparison to the oxygen. So the group 2 and the group 15 have higher ionization energies than expected, so the trend is broken for these. So now let us explain these phenomena. So first of all, why does the ionization energy increase as we go from the left to the right in the periodic table? So now we have to remember again that, as we previously discussed in the last class, that the effective nuclear charge increases as we go from the left to the right in the periodic table. Why is that? Because we are adding additional electrons to the shell, but we are also adding additional protons. Okay, so the electron-proton interaction tends to increase the effective nuclear charge. The electron-electron repulsive interaction tends to decrease it. But because we are adding the electron to the same shell, the latter effect isn't particularly great. Okay, because shielding effects are not particularly strong. Okay, so therefore the effect from the additional proton is larger than the effect from the additional electron. Okay, as a function, as a consequence of that, the effective nuclear charge increases. Okay, so now that increases the binding energy for the electrons to the nucleus. Okay, that decreases the orbital energies, and for that reason it's harder to remove the respective electron from the orbital. Okay, and therefore the first ionization energy increases as we go from the left to the right in the periodic table. Okay, so now why is the trend 2 times broken, one for the group 2 and another time for the group 15 elements? And that is because we have either full subshells or half-full subshells respectively. So for the group 2 elements, the S shell is completely full. And if we, for instance, go from the beryllium to the boron, we have to start a new subshell. So this is energetically not that favorable. So therefore, this new electron, the new subshell, has a relatively high energy and therefore can be relatively easily removed. Okay. Now for the group 15 element, we have a similar effect. So in the group 15, we have a half-filled p subshell, which is also particularly stable. And when we go from the next element, we go to the next element and add an electron, then we are moving away from that very stable half-filled subshell, okay, and destabilizing the electron configuration. So our electrons have a higher energy, and for that reason, we can remove an electron more easily. Okay, so for that reason, the ionization energy decreases as we go from group 15 to from a group 15 to a group 16 element within the same period. Okay, so you see, when you also consider the d elements, that this trend is also true. So the ionization energy increase, but you see that this effect is not as strong as for the main group elements. Okay, so only a very weak increase overall takes place. Okay, almost none, and that is now because within the within the transition metals, we are filling d subshells, okay, which have a lower quantum number n. Okay, so therefore we're adding electrons to an inner shell and not to the same shell. Okay, so now these electrons can shield significantly better. Okay, so therefore the effective nuclear charge doesn't increase as much as for the main group elements. Okay, so you see that this is explaining the behavior of the the D block, and you see that essentially the same is true also for the F block. So also for the F block, we are adding new electrons to an inner shell, okay, where that electron can shield the effective nuclear charge very effectively, and therefore only a very weak increase of first ionization energy is observed for these elements. Okay, so this is the first trend. Now what else can we see? So we can see that when we start a new shell, then our ionization energy drops dramatically. So how can we explain this? Well, when we start a new shell, then we add an electron. Then this electron is much further away from the nucleus, okay, because we start a new shell, and all the other electrons shield the nuclear charge very effectively from that new electron. And for that reason, that new electron has a much higher energy, and for that reason it can be removed much more easily, explaining the low ionization energy. Okay, so the second trend is always when we start a new shell, then the energy is ionization energy is substantially reduced. Okay, so now what else do we see? Well, we see that down a group, the ionization energy tends to decrease. So for instance, as we go from the helium to the neon, to the argon, to the krypton, to the xenon, we see that the ionization energy decrease. So we can explain this trend just as a result from the first two trends that add up. So the first trend tends to increase the ionization energy with increasing atomic number, but the second trend dramatically decreases the ionization energy, and the second effect is somewhat larger than the first effect, and that explains why our ionization energy decreases as we go down a particular group. Okay, so now let's move from the ionization energy, first ionization energy, to be precise, to the electron affinity. So the electron affinity is defined as the energy required or released, okay, to add an electron to a neutral atom in the gas phase. Okay, so first of all, it's important to note that we are again looking at an isolated atom in the gas phase. Secondly, it is important to note that now the process is not always endothermic. It can be either endothermic or exothermic. Okay, in most cases, the process is exothermic. Okay, so the addition of electron to a neutral atom is exothermic, but not in all cases. Okay, so generally, electron affinities are also significantly smaller than ionization energies. Okay, so they're in the order of a few hundred kilojoules per mole, where first ionization energies, we can go back here and look at this scale, are typically in the order of, well, many hundreds to a few thousand kilojoule per mole. Okay, so now let us look more closely at the periodic trends. And you see that it's much harder to define periodic trends for the electron affinity from this graph here in comparison to the ionization energy, and that indicates that the electron affinity is determined by multiple factors that are interact with each other in a more complex way. Okay. So what we generally see, though, that there is some weak trend for the increase of the electron affinity with increasing group number within a period. Okay, so you see, for instance, as we go from the hydrogen to the fluorine, there tends to be somewhat an increase, but you see also that the trend is many times broken. Okay, so if you go from the sodium to the chlorine, you see also there's generally an increase, but again the trend is actually often broken, and you see this trend for the higher periods as well. Okay, but you also see that if you go from the group 7 elements to the group 8 elements, as group 17 elements to the group 18 elements, then there's a dramatic decrease in electron affinity. And in fact, the electron affinities for the noble gases like helium, neon, argon, krypton, xenon are actually negative. Or well, they're actually positive if you define it as an endothermic process. Okay, so it actually requires energy to add an electron to a helium atom or neon atom or an argon atom or a krypton atom, and that's also easy to understand because the noble gases, they have a full shell, and to add an electron to a neutral noble gas, well, it has to start a new shell, and that is of course extremely unfavorable energetically. So it's actually an endothermic process, and the respective anion would not be stable in the gas phase. It would spontaneously emit the electron again. Okay, that is also a reason why electron affinities are experimentally much harder to measure, especially when you're talking about positive electron affinities. Okay, you see that also other elements have positive electron affinities. So, for instance, the nitrogen has a slightly positive electron affinity, and we can again explain this by the fact that the nitrogen has a half-filled subshell, which is fairly stable, and that adding an electron to that half-filled subshell is an energetically unfavorable process. Okay, and therefore the respective anion is not stable. It spontaneously disintegrates in the gas phase. So you see also that for other elements there are a similar effect. So for instance, when you look at zinc, you see that zinc is also having a positive electron affinity. And you can explain this by the fact that in zinc, you have a full 3D subshell. And when you add an electron to a neutral zinc atom, then you have to fill it into a new subshell, which energetically not a very favorable process. Okay, so you see that the same is true actually for the higher homologue cadmium, for example, and even more so for the mercury as an element. So therefore, the only real periodic trend that we can see here is that the electron affinity increases within a period from the left to the right in the periodic table. But the trend is often broken for various reasons. Elements tend to have a negative electron affinity, but some electron affinities are positive. And that's always the case when the atoms have a particularly stable electron configuration, such as a completely full shell in the case of the noble gases, a completely full subshell, as for example in the case of the zinc, or half-filled subshell, as in the case of the nitrogen. Okay, so now let us move over from the electron affinity to a related concept, which is the electronegativity. So the electronegativity has a different name, but it is defined somewhat differently. So the electronegativity is the measure of the ability of an atom to attract electrons in a chemical bond. Okay, so we're still looking at the ability of an atom to attract an electron, okay, but in contrast to the electron affinity, where we look at an isolated atom in the gas phase, we are looking now at an atom in substance that makes chemical bonds within the substance. So we're talking about the ability of an atom to attract electrons in a chemical bond. So this concept has been introduced by Linus Pauling first to describe the relative polarity of bonds and molecules, and its greatest utility is probably that it can make statements about the nature of the covalent, the nature of the chemical bond. Okay, so electronegativity of elements tells us a lot what kind of bonding we can expect when this respective atom binds to another atom. Okay, but we will talk in detail about this in a moment. To start with, let us look at how Linus Pauling defined the electronegativity. So his thought was that the electronegativity is related to the dissociation energies of bonds. Okay, so he defined an electronegativity difference between two atoms as the geometric means of the dissociation energy of a bond AB minus the dissociation energy of a bond AA times the energy of a bond BB. Okay, so he argued that the energy difference between the heteroleptic bond and the homoleptic bond defines the degree of polarity within the bond, which is related to the different ability of the atoms to attract the electrons within the chemical bond. Okay, so now according to this idea, we are only getting electronegativity differences, not absolute electronegativity values. So you must define a reference point. And Pauling defined the reference point to be the fluorine, and he assigned arbitrarily a value of 4 to the electronegativity of the fluorine, and he ordered all the electronegativities of all the other elements relative to the electronegativity of the fluorine. Okay, so now you see here in this graph the electronegativities of the elements in the periodic table. You should first note that in the Pauling electronegativity scale, the noble gases don't have an electronegativity. This is because the noble gases don't make bonds. Okay, so when the element doesn't make bonds, you cannot define bond energies in a meaningful way, and then you cannot define an electronegativity value. But putting the noble gases aside, what trends can we see? So we can see, first of all, that the electronegativities increase within a period, and you see that in contrast to the ionization energy, where we had the same trend, the trend is never broken. Okay, from group 1 to group 17. So we see again that whenever we start a new period, that the electronegativity drops dramatically. So for example, it drops dramatically as we go from the fluorine to the sodium, or from the chlorine to the potassium. So that overall, within a group, the electronegativity decreases down a group. So for instance, for the first group, the electronegativity decreases from the hydrogen to the lithium to the sodium to the potassium to the rubidium and to the cesium. Okay, so that makes cesium the most electropositive, or the least electronegative element. It has a value of about 0.7, while fluorine here at the other end is the element with the highest electronegative value of 4.0. Okay, so you see that this trend, the last trend of the electronegativity decreasing down a group, is strictly true for the main group elements, but it's not quite strictly true for the transition metal elements. In fact, some transition metal elements of the sixth group can actually have quite high electronegativity values. So the gold is the transition metal with the highest electronegativity value. It has an electronegativity value of about 2.4. And you see that this value is comparable with the electronegativity of some non-metals which are much farther to the right in the periodic table. So you see that, for instance, iodine has an electronegativity which is similar in comparison to that of sodium. Okay, so that has interesting consequences, which is that an element like gold can sometimes create ionic crystals. So for instance, when you combine gold with cesium in a compound to make CSAU, to your surprise, you're not getting a metallic compound, you're getting an ionic compound, and that is because of the large electronegativity difference between the cesium and the gold. Okay, now let us look at a few other electronegativity scales, but the Pauling scale the Pauling scale was the first scale, and it's actually still the most popular scale, but it doesn't relate the electronegativity to the quantum mechanical properties of the atom. It derives electronegativities empirically from bond dissociation energies. So therefore, after Pauling, other electronegativity scales were developed that link electronegativity to quantum mechanical properties of the atom. So one is the concept of Allred and Rojo, which relates the electronegativity to the effective nuclear charge over the radius square. Okay, so Z star over R square is actually related to the Coulomb force experienced by an electron on the metal surface. And one would intuitively understand that the higher the Coulomb force is, the greater the ability of the atom to attract electron within a chemical bond. So you see here other factors in front of this term, 3,590 and 0.744. So these are only there in order to make the absolute electronegativity values from the Oort-Rohloff scale comparable to the Pauling scale. So they're just empirically adapted to make the numbers comparable. They have no fundamental meaning. So the second electronegativity scale is the Mulliken scale. Now the Mulliken scale relates the electronegativity to the ionization energy and the electron affinity. Okay, so it says that the electronegativity is proportional to the ionization energy plus the electron affinity. Okay, so we are not too surprised that this works also, because, well, if an atom has a high ionization energy, then as a tendency will probably also have a greater ability to attract an electron within a chemical bond, so its electronegativity will tend to increase. Okay. And if its electron affinity is higher, meaning that it has a now high affinity to attract electrons to a neutral atom in the gas phase, then this will also translate to an electron within a chemical bond. And again, this works also, and you see again here factors in front of this term here, 0.118 minus 0.207. And again, these factors are just chosen in order to make the electron affinity comparable to the original Pauling scale. Okay, so last but not least, there's another concept by Leela C. Allen, which is particularly designed for main group elements. It says that the electron affinity is nothing else but the average electron energies of the p and the s valence electrons. Okay, so mathematical form is the electrons of one p electron times the number of p electrons that exist in that particular atom plus the energy of an s electron times the number of these s electron atoms over the number of all the valence electrons. Okay, so we're not surprised that this also works, because orbital energies are related to ionization energies and electron affinities, and these are also related to the concept of the effective nuclear charge. Okay, in fact, previously we explained orbital energies using the concept of the effective nuclear charge. Okay, so you see that all these different electronegativity scales give you similar results, and they just look at the same issue from somewhat a different perspective. Okay, So now let's go to the application of electronegativity. The biggest application of electronegativity is that it can explain the nature of the bonding within elements, but also within compounds. Let us look at the elements first. You see again here the periodic table. Okay, you see all the metals in blue, the non-metals in green, and you see that the metalloids are in orange. So now I see further the electronegativity values of the elements below the element symbol. So now let us see if we can actually correlate the electronegativity values to the bonding within these elements. Okay, so when the element is a metal, then there will be metallic bonding between the metal atoms. When the element is a non-metal, then there will be covalent bonding between the non-metals. And if we have a metalloid, well, then the bonding will be somewhere in between covalent and metallic. Okay. So can the concept of electronegativity explain that? And the answer is it actually can. You see that when we have metallic bonding, then the electronegativity values tend to be low. They are typically below 2.0, with a few exceptions, for instance, the gold to be named. When the electronegativities are higher than significantly higher than 2.0, okay, you see that for all these elements, then we tend to have a non-metal with covalent bonding in between the atoms. And in addition to that, we now have the metalloids, and you see that for the metalloids, the electronegativity is pretty exactly 2.0. It can be a little bit higher, it can be a little bit lower. Okay. So that means that the electronegativity values can tell you about the nature of the chemical bonding of the elements. So now can we also rationalize that? So now for the metals, we have generally low electronegativity values. So that means within the metals, we have atoms that have little tendency to attract an electron within the chemical bond. Okay, so as a fact, the electrons become actually delocalized, and they're like an electron sea between the atoms. Okay, and that's the most simple picture that we can draw for metallic bonding. Okay, so while for the highly electronegative atoms, like for instance oxygen and fluorine, the opposite is the case. So all the atoms within the element try to draw the electron to themselves. Okay, there's a big battle between the different atoms for the electrons. Okay, and for that reason, the electrons become shared within localized covalent bonds, thereby explaining the covalent bonds. Okay, and for the elements that are metalloids and have kind of intermediate electronegativities, the bonding situation is in between metallic and covalent. Okay, so now I see we are at the end of our time, so let's stop here.